Angular momentum. Before we do this, let us revise the concept of linear momentum, which we had done earlier. P, linear momentum, is given by the product of m, which is the mass, and v is the linear velocity. The corresponding term for linear momentum in rotational mechanics is called angular momentum, and the expression will be L is equal to I omega, where I is the moment of inertia and omega is the angular velocity. And the two types of velocities v and omega are connected with this expression. V is equal to r omega. Now, angular momentum L is a vector quantity. It has magnitude as well as direction. Magnitude is found by the formula L is equal to I omega, but the direction of angular momentum is very important. It is perpendicular to the plane of rotation. And how do we find that? We will be using the right hand rule. Now, let me explain how to find the direction of angular momentum by taking various examples. So, on the bottom left, you can see we have a wheel which is moving in an anti-clockwise direction. How to find the direction of L? We are going to use the right hand. So we are going to curl the fingers in the direction of rotation of this wheel. So this wheel is rotating in an anti-clockwise direction. So imagine the right hand and let's curl in the direction of the wheel. The wheel is rotating in the anti-clockwise direction, and that is what I'm trying to do, curling the fingers in the anti-clockwise direction. So the thumb will give the direction of angular momentum. So let me repeat. We'll be using the right hand. We curl the fingers in the direction of rotation of the wheel, and the thumb then gives the direction of angular momentum. So in this situation, when we curl our fingers in the anti-clockwise direction, so the thumb is actually pointing towards me, which is actually out of the plane. So the direction of L will be towards the person, and we can write that as out of the plane, coming out of the plane. Direction of L first is perpendicular to the plane of rotation. So consider the plane of the screen. L will be perpendicular to the plane of the screen and it is coming towards you. That's for case 1. Case number 2, wheel is now rotating in the clockwise direction. So we do the same thing. Right hand, we will curl the fingers in the clockwise direction. But if we do this, this is anti-clockwise. So we reverse the direction, and now curling of the fingers goes in the clockwise direction so that the thumb is now pointing away from you, away from the person, which is actually going into the screen. So the direction of L in this case will be into the plane. So let me repeat, direction of L is perpendicular to the plane of rotation and it is found by the right hand rule. We curl the fingers of our right hand in the direction of rotation of the wheel, and then the thumb will give the direction of angular momentum. Now let us consider the case 3, another wheel rotating in this direction. Now, what is the difference between this wheel and these two wheels on case 1 and case 2? The first two wheels, consider they are placed on the screen itself. So, plane of rotation of those two wheels are the screen itself. But this wheel has been tilted a little bit. This wheel is not in the plane of the screen. Still, we can use the right hand rule. So, right hand curling the fingers in the direction of the rotation of the wheel. L will be perpendicular to the plane of rotation. And to show the angular momentum in this case, we will draw an arrow like this. This yellow arrow is perpendicular to the wheel and coming out of the wheel as shown in this figure. As opposed to this, let us consider the last case where it is the same wheel but rotating in this particular orientation. Here also we'll do the same thing. Angular momentum direction is perpendicular to the plane of this wheel but found by the right hand rule. So if we curl our fingers in this direction and the thumb will point towards that direction. So this yellow arrow will determine the direction of angular momentum for this wheel. So in exam situation, if we are supposed to find the direction of angular momentum, just remember the basics. It is perpendicular to the plane of rotation, but there are two perpendiculars to the plane of rotation. How do we find that direction? That's found by the right hand rule. As you can see in the last two cases, we have drawn two arrows. Both those arrows are perpendicular to the wheel. So when we say perpendicular to the plane of rotation, there are two arrows possible pointing in the opposite direction as we have seen in the case 3 and case 4. But which arrow is the relevant is determined by the right hand rule. Moving ahead, next topic is Newton's second law for rotation. We had done F net is equal to ma. That's the Newton's second law for linear motion. Acceleration is given by the formula delta v by delta t, since acceleration is the rate of change of velocity. If we put this acceleration expression in this formula, we'll get F net is equal to m delta v by delta t. M into delta v stands for delta p. Remember, momentum is mass into velocity, so m into delta v will be equal to delta p. which is change in momentum. So F net will be delta P divided by delta T. And this expression can be said in the statement form as force is the rate of change of linear momentum. P is the linear momentum. Now let's write down the Newton's second law for rotational motion. The corresponding term for force in rotation is torque. The corresponding term for m in rotational motion is I, moment of inertia. So the expression is torque net is equal to I alpha, where alpha stands for the angular acceleration. Angular acceleration is the rate of change of angular velocity, omega being the angular velocity. And now if we put this expression of alpha in this expression, we will get torque net is equal to I into delta omega by delta t. Now we have discussed angular momentum is I into omega. So I into delta omega will be delta L, change in the angular momentum. So the net torque will be delta L by delta T, which can be written as in the statement form, torque is the rate of change of angular momentum, L being the angular momentum. And based on these formulas, let us try to solve a few questions. Here we have a solid sphere with radius r, mass m. It is rolling along a horizontal surface without slipping with an angular speed omega as shown in the diagram. Which of the following correctly describes the magnitude of the linear momentum of the sphere? We will start with the basic formula for linear momentum. It is given by P is equal to m into v, where v stands for the linear velocity. In the diagram, only angular velocity has been shown. For linear velocity, we can draw an arrow starting from the center and let's say pointing towards the right. Linear velocity is rightward since the wheel is rotating in the clockwise direction. Now, since it is clearly mentioned in the question that rolling is happening without slipping, now remember the rule, whenever this condition is given, V and omega are connected with this formula. V is equal to R omega. So if we replace the expression of V in this formula, linear momentum is just M R omega. And if you look at the options, option A is the right answer to this question. Next off, we have the graph below shows the angular momentum of a rotating solid object against time. Which of the following describes the gradient of the graph? Now, in physics questions, whenever you have graph-based questions, there is only two things which you can do, either gradient or area under the graph, but how to check which one to use where? So remember the trick, gradient is nothing but the division of axis. So y-axis upon x-axis. To be more specific, it needs to be delta y upon delta x. Area, on the other hand, will be the multiplication of the axis y into x. In this question, we are supposed to figure out the gradient. So L, the angular momentum, is on the y-axis, time is on the x-axis. So we can write gradient will be equal to delta y, which is delta L, divided by the denominator will be delta x. X-axis is time, so we will write delta t. And delta t by delta t is the rate of change of angular momentum, and that is nothing but the net torque which is acting on the object. And that is why if we look at the options, gradient of this graph is actually net torque. Hence, D is the answer to this question. Here we have two identical masses M attached to opposite ends of a beam, negligible mass, total length L as shown in the figure. The beam is suspended from its center and it rotates about this vertical axis. Angular speed is omega. And we are supposed to find the magnitude of angular momentum of the system. The system, remember, is made up of two objects, masses m. Let's start with the formula for angular momentum. L is equal to I into omega. So let's start with this m on the right hand side. Angular momentum for this object. Let's label this object as A, and on the left, let's label the object as B. So angular momentum for the object A will be equal to I. I is the moment of inertia, and moment of inertia for an object which is rotating around a circle of radius r, remember, is given by the formula I is m into r square. And if you analyze what will be the radius of rotation for this mass, that is actually half the length of the beam. Because let me try to draw the circle. So m is going to move around in a circle where the diameter will be L. And that is why radius will be L by 2. Since moment of inertia is m into r square, so let's write m. Radius will be L upon 2 whole squared, and angular speed is already given omega. So if we simplify this, we will get m L square omega by 4. Now, don't be in a rush to select option A because that's not the right answer. We have figured out angular momentum only for the object A. For the object B, it is same mass and same distance. So the angular momentum for the object B will have the same magnitude, ml square omega by 4. But remember, angular momentum is a vector quantity. We need direction also. But in this situation, both A and B are moving in the same direction. To analyze that, let's say there is a person looking at this motion from the top end. That person is going to observe A and B both moving in the same circle in the same direction. It is anti-clockwise as we look from the top. So the direction of angular momentum is same for both objects. And since the direction is the same, how do we find the net angular momentum? So let's write down the total angular momentum will be LA plus LB. We are adding the two angular momentums because both objects are moving in the anticlockwise direction. And if we add these two expressions, we are going to get ml square omega by 4 plus ml square omega by 4, which when you simplify gets us ml square omega divided by 2. And now if we look at the options, option B is the right answer to this question. The graph here shows the variation of torque and an object with time. Y-axis is torque, x-axis is time. The moment of inertia is given. Assuming the object starts from rest, what is the final angular speed? Now remember the graph-based concept. If we are given graphs, either we do gradient or the area under the graph. So gradient in this situation will be y-axis upon x-axis. So that will be delta torque divided by delta t. Area, on the other hand, will be the product of torque and time. So which one to use? That will depend on the formula. If you recall the formula for rate of change of angular momentum, delta L upon delta T, that is nothing but torque. Torque is the rate of change of angular momentum. Now, if we analyze the gradient, torque divided by time doesn't mean anything. That is not a parameter. But torque into time means something, because if you look at this expression, let's cross multiply and try to make delta L as the subject. We will get delta L is equal to torque into delta T, which means the area under the torque time graph will give us change in angular momentum. So let me write area for this graph will give us change in angular momentum, and change in angular momentum will be final angular momentum minus initial angular momentum. In the question they have mentioned the object starts from rest. So initial angular momentum will be 0 because angular momentum is nothing but I omega. If the object is at rest, so omega will be 0. Hence, L initial will be equal to 0. So instead of L initial, we'll write 0. For L final, let's write down the formula I omega. So I omega minus 0, that is equal to the area under the graph. And let's try to figure out the area under this graph. So first, let us find the area of this rectangle. Let me shade this entire region. So this is a rectangle whose base length is 8 and the height is 2. So the area of this rectangle will be 8 into 2. So let's write down 16. 16 units will be the area of the rectangle. Next off, we have this triangle whose base is 4. 12 minus 8 is 4 and the height is 2. Area of this rectangle will be half base into height, half 4 into 2, which gets us 4. Hence, area of the triangle is 4. So the total area will be 16 plus 4, which is equal to 20. So let's write down 20 is equal to I into omega. Moment of inertia is given as 0.25. Let's write that down, multiplied by omega. And if we simplify this equation, we will get omega as 80. And since it is angular speed, the unit will be radians per second. And now if we go to the options, the right answer is option D for this question. And that is how we solve graph-based questions. Just remember the concept, either we do gradient or the area in graph-based questions.